Ever wondered how your favorite chewy and hard candies are made? In this behind-the-scenes look, we dive deep into the fascinating world of candy manufacturing. Discover how Sour Patch Kids get their sour punch, how Jolly Ranchers achieve their glassy hardness, and how Haribo gummies come to life, from raw ingredients to the finished sweet treats you love. It all starts with the base formula, the gummy candy itself. The core of every Sour Patch Kid is a soft, chewy matrix primarily composed of sugar, corn syrup, gelatin, and various fruit flavors. These ingredients must be blended in precise proportions to achieve the specific texture that Sour Patch Kids are known for. Not as firm as gummy bears, not as sticky as fruit snacks, but perfectly chewy with a fast melt in the mouth. The sugar and corn syrup form the bulk of the candy. Sugar provides structure, sweetness, and contributes to the candy's crystal clear translucence, while corn syrup prevents the sugar from recrystallizing and keeps the final product soft and elastic. These two are delivered to the factory in bulk, sugar often in rail cars or tanker trucks, and corn syrup in heated stainless steel tankers to maintain fluidity. In the batching area of the facility, massive stainless steel mixing kettles are used to combine sugar, corn syrup, and water. The mixture is heated to dissolve the sugar and initiate cooking. Industrial mixers stir the solution constantly, while steam-jacketed walls evenly raise the temperature to around 230 degrees to 250 degrees, depending on the desired consistency and final moisture content. At this stage, the mixture is highly viscous, resembling hot, liquid sugar syrup. Once the sugar solution is properly cooked, gelatin is added. Gelatin is the key protein that gives Sour Patch Kids their elastic chew. It's derived from collagen, typically from pork or beef, and arrives at the factory as a dry powder. It is hydrated in warm water in separate tanks and added to the sugar syrup only after the syrup has cooled to an appropriate temperature to avoid denaturing the gelatin. This step transforms the hot sugar mixture into a viscoelastic candy base. At this point, citric acid and tartaric acid are introduced. These two organic acids are what provide that first intense sour kick when you bite into a Sour Patch Kid. They are used at very specific levels. Too little, and the candy loses its iconic tang. Too much, and the texture or shelf stability may be affected. Food scientists spend years perfecting this balance. In addition to acidulants, artificial and natural fruit flavorings are also added, usually concentrated solutions of compounds that mimic cherry, lemon, lime, orange, blue raspberry, and other classic flavors. Color is next. Each flavor of Sour Patch Kid is dyed with specific food-grade colorants. These are either synthetic or naturally derived, like beet juice or turmeric extract, depending on the formulation and market regulations. These colorants are added to the mix during the blending phase in tightly controlled amounts to ensure vibrancy and uniformity across batches. Once the hot candy mixture is fully mixed, it is ready to be molded. Sour Patch Kids are molded using a starch mogul system, a technique used for generations in gummy candy manufacturing. The starch mogul line begins with large trays filled with cornstarch. These trays pass under a stamping head fitted with dozens of Sour Patch Kid-shaped molds. The stamps press into the starch, forming hundreds of identical candy-shaped impressions per tray. The hot, syrupy candy mass is poured into these impressions using heated depositors. The candy flows smoothly into each cavity, forming the familiar, tiny humanoid shape. These trays, now filled with thousands of candy molds, are stacked and moved into drying rooms, also known as curing chambers. Here, the candies rest for 24 to 48 hours in warm, dry conditions. The cornstarch helps wick away moisture from the candy, allowing it to firm up without collapsing or becoming sticky. During this curing period, the gelatin sets fully, giving each candy its final chewable texture. After curing, the trays are sent to a destarching station. Here, the starch is separated from the candies using rotating sifters and vibration tables. The excess starch is collected, filtered, and reused in future molding cycles. The Sour Patch Kids, now fully formed and firm, are tumbled through gentle conveyors to remove residual starch. Now comes the most distinctive part of the process, the sour sugar coating. This is what gives Sour Patch Kids their unique mouth-watering appeal. The coating consists of a blend of fine granulated sugar, citric acid, and tartaric acid. The finished candies are placed into large rotating pans or coating drums, similar in appearance to cement mixers, but designed specifically for food products. As the drums rotate, the candies tumble over one another, while a fine mist of water or sugar solution is sprayed lightly to help the sour powder adhere. Simultaneously, the sugar acid blend is sprinkled in. The result is a uniform, crystalline coating on every piece. Timing and rotation speed are key here. Too much coating and the candy becomes overwhelming and sticky. Too little and the signature tang is lost. Factory technicians carefully monitor coating weights and perform quality checks throughout the shift to ensure product consistency. After coating, the candies are passed through a drying tunnel or cooled in ambient air to set the coating. They are then conveyed to an inspection area where cameras, sensors, and sometimes human inspectors check for shape, color, and coating uniformity. Any malformed or off-spec candies are removed from the line. Now it's time to package the final product. Sour Patch Kids are typically packed into portioned pouches, multi-serve bags, or retail cartons. The packaging line begins with form-fill-seal machines, high-speed systems that unroll printed plastic film, form it into pouches, fill each pouch with a measured weight of candy, and then seal it shut using heat. These machines are calibrated to ensure each pack contains the right amount of product and is sealed airtight for freshness. The sealed pouches are then coded with date stamps, batch numbers, and sometimes QR codes for traceability. They are dropped into shipping cartons or display cases, depending on the destination. These cartons are weighed, barcoded, and stacked automatically onto pallets. From there, the pallets move to temperature-controlled warehouses, where they await shipment to stores, vending distributors, movie theaters, and supermarkets. Throughout the factory, food safety is the top priority. Every step, from ingredient receiving to packaging, is conducted under good manufacturing practices. Workers wear protective clothing, hairnets, and gloves. Equipment is cleaned between production runs. Acid-resistant stainless steel and food-grade plastics are used throughout the facility. Environmental controls manage humidity and air filtration to ensure clean room level hygiene in production zones. Sour Patch Kids production also involves detailed analytical testing. Random samples are pulled from each batch and tested in quality control labs for pH, moisture content, acid levels, color uniformity, texture, and shelf life stability. Sensory panels evaluate flavor consistency and sour-sweet balance. If any parameter is off, adjustments are made in the next batch, or the lot is held for investigation. As candy demand has grown, the process has become even more efficient through automation and smart technology. Modern factories use real-time data monitoring systems to control temperatures, mixer speeds, and depositor rates. Predictive maintenance software ensures machinery stays operational. Ingredient inventory is tracked digitally, and computerized dosing systems eliminate human error in weighing acids or colorants. Sustainability has also become a key consideration. Factories producing Sour Patch Kids increasingly aim to reduce water use, lower energy consumption, and source gelatin from suppliers who practice ethical sourcing. Even the packaging films are being redesigned in some regions to be recyclable or biodegradable. When the candy finally reaches store shelves, it has already traveled a long journey, from raw gelatin and sugar to the smiling, sour-coated figures we all recognize. Each bite delivers not only flavor, but the culmination of chemistry, engineering, and candy artistry. The sour then sweet experience isn't just a slogan, it's a precisely engineered sensory journey that begins with a sharp, puckering acid hit and fades smoothly into fruity, mellow sweetness. The process begins with the core ingredients: sugar, corn syrup, water, flavorings, and colorants. These are the building blocks of Jolly Ranchers, but the way they are combined and treated in the factory determines the final product's success. Sugar and corn syrup are delivered in bulk to the manufacturing plant, sugar often in powder or granulated form, and corn syrup as a thick liquid shipped in insulated tanker trucks to keep it warm and flowable. In the batching room, Large stainless steel kettles are used to combine sugar, corn syrup, and a small amount of purified water. The goal is to dissolve the sugar and initiate a high-heat cooking process that transforms these ingredients into a highly concentrated, clear candy base. This cooking step is key. Jolly Ranchers are a type of hard candy, which means the sugar mixture must be cooked to what's known in confectionery as the hard crack stage, around 300 degrees to 310 degrees. These cooking kettles are jacketed with steam coils or electric heating elements that allow precise temperature control. As the mixture heats, the water begins to evaporate and the syrup thickens significantly. This evaporation is critical. It's what ultimately leaves the candy with such a low moisture content that it becomes glassy and brittle once cooled. Industrial stirrers keep the mixture agitated to ensure even cooking and prevent hot spots or scorching. As the syrup approaches the target temperature, automated sensors closely monitor the heat and viscosity. If the temperature is even slightly off, the final texture of the candy could be compromised. Undercooked syrup results in a sticky or chewy texture, while overcooked syrup becomes too brittle or may develop a burnt flavor. Once the sugar syrup reaches the perfect consistency, it's time to add the key components that give Jolly Ranchers their personality: flavor and color. The candy base is divided into smaller batches, each destined to become a different flavor: cherry, watermelon, green apple, blue raspberry, grape, and others. Each batch is transferred to flavoring tanks or mixing troughs where concentrated food-grade flavorings and dyes are added. These flavor compounds are highly concentrated and added in very specific ratios. Natural and artificial flavorings are used depending on the formulation. For example, a cherry Jolly Rancher might include benzaldehyde for that sharp, almond-like cherry punch, while green apple flavor could rely on malic acid esters for its tart kick. The colorants are also carefully chosen to match the expected visual identity of the flavor. Red 40, Yellow 5, Blue 1, and other FDA-approved synthetic dyes are often used in varying combinations to produce the vivid hues. Mixing must be fast and efficient at this stage because the candy syrup is still extremely hot and starts cooling quickly. Mixing arms or ribbon blenders integrate the flavor and color without introducing air bubbles, which would compromise the candy's clarity and structure. At this point, the flavored and colored syrup begins to thicken rapidly and takes on the consistency of hot, pliable taffy. Timing is critical. If it sets too quickly, it becomes unworkable. The next step is forming. Unlike many other candies that are molded in starch trays, Jolly Ranchers are formed using a process known as rope forming and die stamping. The hot candy is transferred onto cooling tables or through temperature-controlled rollers where it is shaped into thick, cylindrical ropes. These ropes are slowly cooled as they pass through stainless steel rollers and conveyors. The goal is to bring the candy down to a workable temperature where it can be cut and stamped, but not yet hardened completely. Once the candy ropes are at the right consistency, they pass through a forming machine fitted with precision dies. These dies stamp and cut the candy into individual pieces, each with the familiar oblong pillow shape. The forming machine applies enough pressure to ensure a clean cut, but not so much that it distorts the candy's surface. This is a delicate operation, as the candy is beginning to crystallize and solidify rapidly. The cutters must be kept heated or treated with food-safe lubricants to prevent sticking and preserve the clean edges of the final product. After forming, the individual Jolly Ranchers move on to a cooling conveyor system. These long, slowly moving belts expose the candies to progressively cooler ambient air or cooled forced air, gradually lowering their internal temperature. This slow cooling is important to prevent cracking and to ensure the surface remains glossy. If cooled too quickly, internal stresses could form, making the candy brittle or causing it to become cloudy. Once fully cooled and solid, the candies head to the wrapping stage. Each Jolly Rancher is immediately wrapped in a specially designed waxed film or polypropylene-based wrapper that prevents sticking and maintains freshness. Wrapping machines operate at extremely high speeds, feeding candies into synchronized rollers that twist wrap or fold seal each piece. The wrappers are pre-printed with branding, flavor indicators, and batch codes for traceability. The wrapped candies are then collected into large bins or counted into packaging units. Depending on the product line, Jolly Ranchers might be bagged into share-size pouches, fun-size treat bags, or bulk cartons. Form-fill-seal packaging equipment handles this part, weighing exact quantities of candies, dropping them into bags formed from a continuous roll of printed film, then sealing the bags with heat to make them tamper-evident and shelf-stable. As the candies are packaged, quality control plays a key role throughout the process. Random samples are taken and tested for color accuracy, size uniformity, hardness, and moisture content. Hardness tests may involve durometers or similar equipment that measures resistance to pressure, ensuring the candy has the right glass-like firmness. Flavor panels may also evaluate taste intensity, checking for flavor balance and clarity. If a batch is found to be off-spec, it may be rejected, reworked, or diverted to secondary markets. Behind all this precision lies rigorous food safety protocols. Workers wear gloves, hairnets, and lab coats in production areas. Machines are sanitized regularly, and allergen controls are in place even though Jolly Ranchers typically contain no nuts, dairy, or gluten. Hazard analysis and critical control point systems are used to identify and mitigate risks at each step of the process. From the moment the sugar is received to the point where a wrapped candy is sealed in a bag, every movement is monitored and recorded for traceability. Additionally, modern Jolly Rancher production facilities are incorporating automation and smart factory technologies. Recipe management systems ensure precise ingredient dosing, and digital controls allow managers to adjust batch temperatures and cooking times from central dashboards. Optical sensors inspect wrappers for misprints. Even the temperature and humidity of production rooms are computer controlled to maintain consistent output regardless of the season or climate outside. Sustainability is also being addressed in newer production lines. Energy-efficient kettles and heat recovery systems help reduce fuel use. Water used in equipment cleaning or steam generation is recycled where possible. Wrapping materials are being developed with recyclability in mind, and many facilities are exploring biodegradable or compostable film options. The finished Jolly Ranchers, now bagged and boxed, are stacked onto pallets and moved into climate-controlled warehouses for distribution. These candies are remarkably stable, with long shelf lives due to their low moisture content and protective wrapping. This makes them ideal for global shipping. From there, they head to supermarkets, convenience stores, vending machines, and movie theaters all around the world, ready to deliver that unmistakable burst of sour cherry, green apple, or blue raspberry flavor. It all begins with the selection and preparation of the raw ingredients. At the core of every Haribo gummy candy is a combination of sugar, glucose syrup, gelatin, citric acid, fruit flavoring, and food coloring. These ingredients must be carefully sourced and managed to ensure the consistent taste, texture, and appearance that consumers expect. Sugar and glucose syrup form the base of the gummy. These are typically delivered to the Haribo factory in large quantities, sugar in bulk containers or silos, and glucose syrup in insulated tankers to maintain fluidity. In the production facility, the sugar and glucose syrup are fed into large stainless steel kettles equipped with steam jackets and stirring paddles. The mixture is gently heated and stirred to fully dissolve the sugar crystals, creating a thick, sweet solution. This sugary base is the fundamental building block for all Haribo products. Once the sugar solution reaches the appropriate concentration and temperature, gelatin is introduced. Gelatin is a key functional ingredient in Haribo gummies, providing their characteristic chewiness and structure. It is typically derived from pork or beef collagen and arrives at the factory in dehydrated granule or sheet form. Before it can be added to the sugar mixture, the gelatin is first hydrated in warm water in separate mixing tanks. Once fully dissolved, the gelatin is combined with the hot sugar syrup under controlled conditions. The resulting mixture is carefully heated to a precise temperature, usually around 150 to 160 degrees, ensuring full integration of the gelatin without degrading its gelling ability. During this step, any acids such as citric acid or malic acid are also added. These acids are responsible for the pleasant tang that balances the sweetness of the candy and enhances the fruit flavors. Next, the flavorings and colors are introduced. Haribo uses a range of natural and artificial fruit flavors to create its signature gummy taste profiles. Each flavor, lemon, orange, raspberry, pineapple, and apple, among others, is blended in concentrated liquid form and carefully metered into separate batches of the hot candy mix. Food-grade colorants are added alongside the flavorings, giving each candy its bright, transparent hue. The combination of flavor and color must be exact to meet Haribo's internal standards, and flavor technicians often perform sensory evaluations during production. With the flavored and colored syrup fully prepared, it is ready for the molding process. Haribo gummies are formed using a traditional confectionery technique known as starch molding, or the starch mogul system. This process begins with large trays filled with cornstarch. A molding board presses bear-shaped cavities into the surface of the starch, creating hundreds of individual molds per tray. The hot, viscous candy mixture is poured into these molds using automated depositors equipped with multiple nozzles. Each nozzle dispenses the exact volume of syrup needed to fill a single bare cavity, ensuring uniform size and weight across thousands of pieces. The trays are then stacked and transferred to a curing room, a warm, dry environment where the candies are allowed to set for 24 to 48 hours. During this curing period, the gelatin network solidifies, giving each gummy its final elastic texture. The starch not only supports the shape, but also absorbs moisture from the surface of the candy, helping to achieve the perfect skin. Once the gummies are fully cured, the trays are sent to a destarching machine. This piece of equipment gently tumbles the trays, separating the candy pieces from the cornstarch. Vibrating screens and air jets remove any excess starch, which is collected, filtered, and reused in the molding process. The newly formed gummies, now free of starch and fully set, are inspected and prepared for the next stage. Now comes the coating process, which adds shine and improves handling. Haribo gummies are typically coated with a thin layer of food-grade wax, such as carnauba wax or beeswax, and vegetable oil. This coating is applied in rotating drums or tumblers, where large quantities of gummies are gently mixed while a light mist of the wax solution is sprayed over them. The result is a glossy surface that prevents the candies from sticking together and enhances their visual appeal. The wax also serves as a moisture barrier, helping to preserve the candy's freshness during storage and transport. After coating, the gummies pass through a final inspection phase. This includes both visual inspections by trained staff and automated optical systems that check for shape uniformity, color consistency, and size accuracy. Any defective or malformed candies are removed from the line and discarded or recycled, depending on the facility's protocols. Next, the candies move on to the packaging line. Haribo uses a range of packaging formats, including peg bags, share-size pouches, single-serve packs, and multi-flavor assortments. The packaging process begins with high-speed form-fill-seal machines. Printed plastic film is unrolled and shaped into pouches, which are then filled with a precise weight of gummies. The bags are sealed using heated jaws that bond the plastic layers together, creating an airtight, tamper-evident package. The filled bags are then printed with production information such as batch number, expiration date, and sometimes promotional codes or QR codes for consumer engagement. They are packed into cartons, stacked onto pallets, and moved to the warehouse where they await distribution. Throughout this final stage, quality control teams monitor the sealing integrity, fill weights, and print accuracy to ensure compliance with product specifications. Behind the scenes, every Haribo production facility operates under strict food safety and quality assurance protocols. These include adherence to good manufacturing practices, hazard analysis and critical control points, and ISO quality standards. Production areas are cleaned regularly, equipment is sanitized, and every batch is traceable from raw ingredient to finished product. Samples are pulled at every stage and tested in on-site laboratories for pH, moisture content, texture, and microbial safety. Modern Haribo factories also make use of advanced automation and data analytics. Ingredient dosing is controlled by programmable logic controllers to reduce human error. Sensors monitor cooking temperatures, gelatin concentration, depositor output, and humidity levels in real time. Production managers can access digital dashboards to track performance metrics and respond quickly to any deviations. These innovations not only improve efficiency, but also support the consistency that Haribo is known for. As a global brand, Haribo also customizes its recipes and flavors for different regions. For example, gummies produced in Europe may use natural colorings derived from fruit and vegetable concentrates, while US products may include certified synthetic dyes. Flavors may also vary to suit local preferences, such as blackcurrant in the UK, mango in Asia, or sour varieties in North America. Despite these differences, the core manufacturing process remains largely the same across all Haribo facilities. Sustainability is another growing focus in Haribo's operations. The company has been investing in renewable energy, water conservation, and waste reduction across its factories. Ingredient sourcing increasingly considers environmental impact and animal welfare, particularly in the sourcing of gelatin. Packaging materials are being re-evaluated to include recyclable films and reduce plastic usage. When a bag of Haribo Gold Bears finally lands on store shelves, it represents a highly coordinated blend of traditional candy-making techniques and modern industrial precision. Each chewy bear is the product of strict formulation, controlled cooking, precise molding, and sophisticated quality checks. From sugar kettle to glossy, colorful treat, the journey of a Haribo gummy is a testament to the art and science of confectionery manufacturing. While the candies may be playful and whimsical, the process behind them is anything but casual. It requires the coordination of food engineers, quality control experts, maintenance technicians, flavor developers, and packaging specialists, all working together to ensure that every handful of Haribo delivers the same beloved taste and texture, whether it's made in Germany, the United States, or anywhere else Haribo operates. This level of consistency and care is what has allowed the brand to thrive for over a century, making Haribo gummies a global favorite that continues to delight generation after generation. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step, cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids, and are now ready for the next phase, grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel, where the caramel layer is firm to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients: glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings, are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor brix levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations, including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. It all begins with the chicken itself, fresh, never frozen, and selected according to strict specifications that have been standardized over decades. At the heart of KFC's fried chicken production is consistency, and that starts with sourcing poultry from highly regulated farms, often contracted directly to supply birds that meet stringent criteria for weight, size, age, and health. These chickens are typically raised under controlled conditions, with monitored feeding schedules and veterinary oversight, ensuring uniformity in muscle development and fat content. Farmers work closely with the suppliers to deliver birds that fall within the optimal range for processing, which generally hovers around 4 to 6 pounds per whole bird, depending on the regional market. Once the birds arrive at the poultry processing plant, they undergo a sequence of highly regulated steps designed to transform them into the individual cuts used in KFC's iconic fried chicken buckets. The first step is stunning and slaughter, where automated systems humanely render the birds unconscious before they are swiftly slaughtered. This is followed by scalding, immersing the carcasses in warm water to loosen feathers, and defeathering using a mechanical plucking system that employs rotating rubber fingers to strip feathers from the skin without damaging the flesh. The next phase involves evisceration, where internal organs are removed through a series of automated mechanical arms and cutting systems. Inspectors, both human and digital, examine the internal cavities for any signs of disease or contamination. The birds are then washed thoroughly in a series of chilled water baths and antimicrobial sprays to reduce surface bacteria. After this, the carcasses are chilled rapidly, often through immersion in ice water or air chilling tunnels, to bring the internal temperature down to safe levels before further processing. With the whole birds chilled and inspected, they are transferred to the cutting line. This is where the chicken is portioned into the familiar cuts used in KFC recipes: drumsticks, thighs, breasts, wings, and occasionally rib portions, depending on the market. High-speed blades and vision-guided robotic systems ensure that each piece is cut uniformly. Some facilities even use X-ray and laser-guided cutting to detect bone structure and fat lines, optimizing yield and reducing waste. The chicken pieces are then sorted by size and weight, ensuring every batch has a consistent mix for packaging and preparation. After cutting, the chicken is placed into sanitized plastic totes or stainless steel trays and sent to the marination area. This is a crucial step that lays the foundation for KFC's signature flavor. The original recipe chicken is soaked in a wet brine that typically includes water, salt, and phosphate-based tenderizers to enhance juiciness and flavor retention. The chicken is placed into large tumblers, rotating drums with paddles inside that gently agitate the meat to ensure thorough penetration of the brine. This marination process typically lasts for a fixed duration, anywhere from 30 minutes to several hours, depending on the specific product line. But marination is just the beginning. What truly sets KFC apart is the breading process, a meticulously controlled step where secrecy and technique intertwine. The chicken is removed from the brine and allowed to drain slightly before being transferred to the breading stations. The breading mixture, known for its secret blend of 11 herbs and spices, is kept under strict control. At the manufacturing level, this seasoning is produced in centralized spice blending facilities, measured with pharmaceutical-level precision, and shipped to stores or distribution centers in tamper-proof bags. Operators follow a carefully choreographed breading procedure known as the 7-to-10-7 method. First, the chicken is placed into a flat metal pan with the dry breading mix and hand-tossed 7 times in a specific pattern to ensure an even coating. Then the pieces are compressed down into the breading mixture for 10 seconds. This step helps the coating adhere and creates the famous textured crust. Finally, the pieces are shaken 7 more times and arranged neatly onto perforated trays for the next stage. This manual method, despite being labor-intensive, is a cornerstone of KFC's identity and helps achieve the distinctive craggy exterior that customers recognize instantly. Once breaded, the chicken is moved to the fryers. KFC uses high-capacity pressure fryers, commercial machines that resemble deep fryers, but with tightly sealed lids that allow cooking under pressure. This equipment is critical for achieving the brand's signature texture: crispy on the outside, juicy on the inside. The sealed environment traps steam from the chicken's internal moisture, cooking it rapidly while locking in juices. The breaded pieces are loaded into metal baskets, which are then placed into the preheated pressure fryers filled with proprietary frying oil blends, typically high in stability and low in trans fats. Each fryer is pre-programmed to precise cooking parameters, controlling temperature and time based on the chicken type: bone-in, boneless, tenders, or wings. For original recipe bone-in chicken, the typical cooking cycle runs around 10 to 15 minutes at roughly 325 degrees under pressure. As the pressure builds, the internal temperature of the chicken rises quickly, reducing cook time while preserving moisture. Throughout the cooking process, sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration, ensuring every batch turns out uniform and safe to eat. Once cooking is complete, the fry baskets are lifted automatically or by hand, and the chicken is allowed to drain for a brief period over the oil vat. Operators then transfer the finished product to a holding station, typically a heated cabinet or a moisture-controlled drawer that maintains the chicken at a safe temperature, usually above 140 degrees F, while preventing the crust from getting soggy. These holding cabinets are set to timers that ensure chicken is only kept for a limited time before it is discarded or rotated out, reinforcing KFC's strict freshness policy. Throughout this entire process, food safety is paramount. Every station is equipped with hand-washing sinks, sanitizer dispensers, and cleaning schedules that are enforced hourly. Employees wear gloves, aprons, and hairnets or caps, and facilities conduct routine microbial testing on surfaces and air to minimize contamination risks. Temperature logs, batch records, and fryer oil quality checks are performed regularly. The oil itself is filtered several times per day using built-in filtration systems that remove particulates and extend the oil's usable life while maintaining flavor quality. But the process doesn't begin or end in the kitchen. At the supply chain level, KFC relies on a cold chain network that keeps the chicken and ingredients at safe temperatures from the processing plant to the store. After the chicken is marinated and portioned at regional facilities, it is vacuum sealed or packed into airtight food-grade plastic bags, then stored in refrigerated trucks with active temperature tracking systems. GPS-enabled trailers ensure the logistics team can monitor both temperature and location in real time, avoiding spoilage or delays. The spice blends, breading flour, oil blends, and packaging materials are all shipped through similarly optimized networks, allowing stores to receive fresh inventory on a scheduled basis without interruption. When the chicken finally reaches the individual KFC restaurants, it is stored in walk-in coolers, prepped according to the exact procedures laid out by corporate training, and cooked fresh on-site throughout the day in small batches to keep up with demand. The entire system is designed for scalability and control. From a small store in a rural town to a flagship location in a major metropolis, the chicken tastes almost identical. That's the power of systematized food production at scale. Interestingly, much of KFC's fried chicken production still retains a manual, human-guided feel despite the high-tech systems that support it. While robotics and automation are increasingly common in many fast food chains, KFC's breading process continues to rely heavily on trained workers. This combination of human skill and industrial precision contributes to the unique texture and flavor of the final product. It all begins with the raw materials. At the core of the Big Mac are its two beef patties, 100% pure ground beef with no fillers, additives, or preservatives. These patties are made from specially selected cuts of beef, typically chuck, round, and sirloin, all blended to achieve McDonald's-specific fat-to-lean ratio, usually around 80-20. The cattle are sourced from approved ranches and farms, where animal welfare, feed quality, and traceability are tightly controlled. These suppliers operate under strict auditing and food safety programs to ensure consistency and safety throughout the entire supply chain. At the beef processing plants, the meat is first received in chilled form and stored in temperature-controlled environments. It then moves to large-scale grinders where the cuts are ground to a uniform consistency. The grinding process uses precision-engineered machinery that not only ensures even texture, but also mixes the fat content evenly throughout the meat. After grinding, the meat is portioned into exact patty sizes using high-speed forming equipment. Each Big Mac patty is a 1.6-ounce round that measures precisely to fit the 3-part sesame seed bun. Once the patties are formed, they are immediately flash frozen using cryogenic tunnels or spiral freezers. This locks in moisture and prevents microbial growth while maintaining the structural integrity of the patty. The frozen patties are then stacked into cartons, sealed, and loaded into refrigerated trucks that maintain a cold chain at all times. They are shipped to McDonald's distribution centers, which in turn supply local restaurants with scheduled deliveries to ensure freshness and efficient inventory management. But a Big Mac isn't just beef. Another critical component is the famous 3-part sesame seed bun: the crown, the club, and the heel. These buns are produced in large-scale commercial bakeries that specialize in McDonald's specifications. The dough is made from wheat flour, water, yeast, sugar, and conditioners to ensure softness and volume. The mixing and proofing process is closely monitored by computerized systems that control dough temperature and humidity. Once proofed, the dough is portioned into perfectly sized balls and dropped into custom baking molds designed specifically for the Big Mac's 3-part structure. The top bun is topped with sesame seeds just before baking. Conveyor ovens bake the buns at precisely calibrated temperatures for consistent color, texture, and internal moisture. After baking, buns are cooled on spiral cooling racks, then sliced, and the 3 segments are separated and packaged accordingly. Like the patties, the buns are then flash frozen or refrigerated and shipped to McDonald's outlets. Another defining component of the Big Mac is its sauces and toppings, specifically the Big Mac Special Sauce. The exact formula is proprietary, but the flavor is unmistakable. A tangy, creamy, slightly sweet sauce that combines elements of mayonnaise, mustard, relish, garlic, onion powder, and other spices. This sauce is manufactured in centralized condiment processing facilities, where ingredients are blended in large stainless steel tanks using industrial mixers that maintain a homogeneous emulsion. The final product is pumped into sealed, portion-controlled containers that are shipped cold to restaurants. In addition to the sauce, there are sliced pickles, dehydrated onions that are rehydrated on-site, shredded iceberg lettuce, and American cheese. The pickles are cut from whole cucumbers and brined in tanks with a proprietary vinegar and spice solution. They're sliced to a uniform thickness, then packed in brine to retain crunch and flavor. The onions come pre-chopped and dehydrated to extend shelf life and reduce spoilage. They are soaked in cold water at the store level before use. Lettuce is shredded in controlled processing plants and packed into vacuum-sealed bags. It must meet specific dimensions for length and width to ensure even coverage and manageable volume in the sandwich. The cheese, a processed slice tailored for meltability and flavor stability, is individually wrapped and delivered refrigerated. At the restaurant level, the Big Mac is assembled in a precise, time-tested sequence designed for speed and uniformity. When a customer places an order, the kitchen system relays it to the grill and assembly line. The patties are cooked on a dual-sided clamshell grill, a piece of kitchen equipment that cooks both sides of the patty simultaneously. This reduces cook time to less than a minute, while ensuring the internal temperature reaches the USDA required safe zone of 155 degrees Fahrenheit or higher. The grills are calibrated multiple times a day to maintain consistent heat, and they include timers and temperature sensors that alert the crew when patties are done. Simultaneously, the buns are toasted on a vertical conveyor toaster that crisps the inside surfaces while leaving the exterior soft. Each bun, top, middle, and bottom, is inserted into a specific slot in the toaster, ensuring that they emerge in the correct sequence for stacking. The bun toaster is also calibrated for toast color and surface temperature, both of which affect the texture and structural integrity of the final sandwich. Once the patties and buns are ready, the assembly begins on a stainless steel prep table or station called the sandwich build line. Each component is added in exact order. The heel receives a half teaspoon of rehydrated onions, followed by shredded lettuce, 1 slice of cheese, and the first cooked beef patty. The middle bun is then placed on top, followed by a second layer of sauce, onions, lettuce, and pickles, then the second patty. Finally, the top bun is placed to crown the entire structure. Employees are trained to assemble the Big Mac with a high degree of consistency, using scoops and dispensers designed to deliver precise amounts of sauce, lettuce, and onions. Visual guides are often posted above the station, and training involves repetition to internalize the build order and portion sizes. Speed is crucial, but accuracy takes priority. Each Big Mac must be indistinguishable from the next. Once assembled, the sandwich is wrapped in specially designed cardboard clamshells or wrappers that help maintain heat without causing sogginess. These are placed in warming areas or immediately bagged for customer pickup, depending on the workflow of the kitchen. Each Big Mac is usually served within a 5 to 10 minute window of cooking, ensuring it is hot, fresh, and true to form. Food safety and quality assurance are embedded in every stage of this process. The patties are temperature checked with digital thermometers. Sauce containers are labeled with use by times. Lettuce and onions are discarded after a certain number of hours out of refrigeration. Crew members follow strict hygiene protocols, including hand washing every hour, wearing gloves, and rotating utensils to prevent cross-contamination. Regular audits and surprise inspections ensure compliance with these standards. McDonald's kitchens also operate with a high level of automation and integration. Point-of-sale systems are linked to kitchen monitors, which display order sequences in real time. Inventory systems track ingredient usage and automatically flag restocking needs. Even the toaster and grill equipment is connected to central management systems that log performance data, usage cycles, and maintenance schedules. Behind the scenes, logistics play a crucial role in Big Mac production. From farm to fryer, the ingredients move through a vast cold chain network supported by regional distribution centers. These hubs maintain constant temperature control and manage stock rotation to ensure that every restaurant has fresh, usable inventory. McDonald's works closely with third-party logistics companies and in-house supply teams to coordinate deliveries across thousands of outlets every day. Even sustainability is being integrated into the Big Mac's life cycle. McDonald's has committed to sourcing beef more responsibly, using packaging materials that are recyclable or compostable, and reducing waste in the supply chain. Many of the buns are baked in facilities that run on renewable energy, and fryers now use low-emission heating systems. The lettuce and pickles are sourced from farms that practice water conservation and integrated pest management. In the end, the Big Mac is more than a sandwich. It's a manifestation of precision food engineering on a global scale. What might seem like a simple fast food item is the result of decades of refinement in agriculture, logistics, processing, and food safety. The carefully orchestrated choreography of farmers, food scientists, line cooks, and engineers ensures that every customer experiences the same taste, texture, and satisfaction with every bite. Whether it's the sizzle of the patties on the grill or the final crown of the sesame bun, every step is designed to deliver that unmistakable Big Mac experience. It all starts with the dough. Domino's dough is made in regional commissaries, large-scale production facilities that supply fresh dough to stores several times a week. These commissaries receive shipments of high-quality wheat flour from trusted grain suppliers. The flour, typically enriched and with a mid-range protein content around 12%, is combined with water, yeast, salt, sugar, and a small amount of oil in massive stainless steel mixers. These mixers, with capacities ranging from hundreds to thousands of pounds, mix the dough until it reaches the desired elasticity and gluten development. The dough is then allowed to rest and rise in temperature and humidity-controlled proofing rooms. These chambers regulate fermentation precisely, letting the yeast activate and produce carbon dioxide, which is what gives the dough its airy structure. This stage is not rushed. Domino's prioritizes flavor and texture, allowing the dough to ferment for several hours or even overnight to develop deeper taste and a balanced chew. After proofing, the dough is portioned into individual balls using industrial dough dividers and rounders. Each ball is scaled for the correct pizza size: small, medium, large, or extra large, and placed into trays lightly coated with cornmeal or oil to prevent sticking. These trays are stacked into rolling racks and moved into refrigerated holding rooms. Chilled to slow further fermentation, the dough balls are now ready for transport. They're boxed, loaded into cold chain delivery trucks, and shipped to Domino's outlets across the region on a tightly managed delivery schedule. Now comes the tomato sauce, an essential component that gives every pepperoni pizza its acidic punch and signature flavor base. The sauce is made at centralized processing plants using vine-ripened tomatoes, typically harvested at peak season and steam peeled for optimal flavor preservation. The tomatoes are ground and mixed with a proprietary blend of spices, including oregano, basil, garlic powder, onion powder, salt, and sometimes a pinch of sugar to balance acidity. This sauce is then pasteurized to ensure shelf stability and safety, and filled into sealed plastic pouches or buckets, which are shipped refrigerated to each Domino's location. Cheese, too, is a cornerstone ingredient in every pepperoni pizza. Domino's uses a special low-moisture, part-skim mozzarella blend developed for optimal melt, stretch, and browning. Large cheese manufacturing plants shred or dice the mozzarella into uniform pieces that fall easily onto the pizza and melt consistently. The cheese is bagged, nitrogen flushed to prevent spoilage, and stored cold until it's needed. Domino's has strict cheese specifications that regulate fat content, meltability, and even browning color curves during baking. And of course, there's the pepperoni. Domino's pepperoni is a type of cured, spiced sausage made from a mix of beef and pork. The meat is ground and blended with a spice mixture that includes paprika, garlic, crushed red pepper, fennel seed, and curing salts. After being emulsified, the mixture is stuffed into collagen casings and fermented to develop its tangy flavor profile. The pepperoni is then slow-dried, sometimes smoked, and aged until it reaches the correct firmness. Once matured, it's sliced into perfect, thin rounds that crisp slightly when baked but retain their juicy center. These slices are packed into refrigerated cases, typically with a layer of wax paper to prevent sticking, and distributed to stores for daily use. At the store level, the pizza making process begins when an order is received, either online, via app, or in-store. The store crew retrieves a dough ball from the walk-in cooler and places it on a prep table dusted with cornmeal or flour. Unlike hand-tossed pizzerias, Domino's uses a combination of manual and mechanical techniques to stretch dough. The dough ball is pressed using a dough press or roller to achieve the correct size and thickness. Then it may be hand-finished to achieve an even round shape with a defined edge, or cornicione. Once the crust is prepared, the pizza moves down the make line. A ladle of tomato sauce is spread in a spiral motion from the center outward, leaving a consistent border around the edge. Precision here is key. Too much sauce and the crust gets soggy. Too little and the pizza lacks flavor. Domino's uses portion-controlled utensils to ensure uniform application across thousands of pizzas a day. Next comes the cheese. Employees grab pre-measured amounts of shredded mozzarella from cold bins and scatter it evenly over the sauced crust, making sure to reach the edges to maximize melt and appearance. The cheese-to-sauce ratio is carefully designed to complement the crust thickness and baking conditions in the oven. Domino's often uses cheese guides or weight scales to prevent under or over application. Then it's time for the pepperoni, the star of the show. Domino's applies pepperoni in a uniform pattern, usually a ring-based layout that ensures each slice of the final pizza gets equal coverage. The pepperoni is placed on top of the cheese so it crisps and curls slightly during baking, creating those little greasy, flavorful cups that have become a hallmark of American pepperoni pizza. The number of pepperoni slices is not left to chance. Domino's has precise count targets per size, such as 30 slices for a medium and 40 for a large, ensuring every customer receives the expected experience. Once built, the raw pizza is placed onto a pizza screen or baking tray and sent into a conveyor oven. Domino's signature baking method. These ovens, called impinger ovens, are long, tunnel-like machines that use jets of superheated air to cook the pizza quickly and evenly. The oven belt moves at a fixed speed, typically cooking a pizza in about 6 to 7 minutes at a temperature of approximately 465 degrees Celsius to 500 degrees. The impingement cooking method forces hot air onto the top and bottom surfaces of the pizza simultaneously, ensuring a crisp crust and melted, browned cheese with consistent results. As the pizza exits the oven, crew members perform a quick visual check for doneness. The cheese should be fully melted and bubbling, the pepperoni slightly curled with crispy edges, and the crust golden brown. The baked pizza is transferred to a cutting board and sliced with a rolling blade into even segments, typically 8 for a large pizza. The blade is wiped between uses to prevent sauce and cheese buildup. The pizza is then placed into a specially designed Domino's pizza box made from recycled corrugated cardboard. These boxes are ventilated to allow excess steam to escape, preventing sogginess during delivery. Each box is folded and branded with Domino's blue and red logo and has space for order stickers, promotional labels, and QR codes. A thermal lining or pizza insert may also be used in some regions to help retain heat during transport. Once boxed, the pizza is either handed over to a customer in-store or placed into an insulated delivery bag. These bags are engineered to retain heat and allow limited airflow, keeping the pizza hot but not steamy. Domino's delivery drivers follow optimized GPS routes generated by proprietary software that prioritizes speed and traffic conditions. Many stores use heat racks or warming stations to hold pizzas briefly while waiting for drivers or curbside pickup. Behind the scenes, Domino's uses sophisticated technology to monitor every step. The point-of-sale system automatically tracks inventory levels. Real-time analytics inform store managers about the number of pizzas being ordered, the time each step takes, and potential bottlenecks. Domino's Pizza Tracker gives customers live updates on the progress of their order, from prep to baking to out for delivery, driven by timestamps and kitchen inputs. Cleanliness and food safety are integral to every stage. Dough trays and utensils are washed in commercial dish machines between uses. Gloves are worn and changed frequently. Prep stations are sanitized regularly throughout the day. All cold ingredients are stored in reach-in coolers with thermometers to maintain optimal temperature. Internal audits and third-party inspections ensure compliance with food safety standards and corporate procedures. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. the sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, Heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. The production of Cheetos begins not with cheese or seasoning, but with one humble ingredient: corn. In fact, the specific type of corn used in Cheetos manufacturing is carefully selected and processed to meet exacting technical standards before it even enters the plant. The base product of every Cheeto is degermed cornmeal, derived from a variety of field corn that is specially cultivated for its high starch content and low fat levels. This corn must produce a uniform, predictable puff when subjected to extreme heat and pressure, so its density, moisture content, and kernel hardness are closely monitored even at the agricultural stage. Farmers contracted by the manufacturer are required to meet tight tolerances in grain quality, harvesting methods, and post-harvest drying to ensure the raw corn will meet the standards for industrial puffed snack production. Once harvested and transported to the ingredient supplier, the corn undergoes an initial cleaning to remove plant debris, soil, and foreign materials. It is then taken through a degermination process, in which the outer bran layer and the germ, the oil-rich, nutrient-dense part of the corn kernel, are removed. This step is essential. While germ and bran contain healthy fats and proteins, their presence can negatively impact the expansion properties and shelf life of the final product. Germ oil can go rancid over time and interfere with the consistent puff structure that defines a Cheeto. What remains after degermination is the starchy endosperm, milled down into a fine cornmeal that becomes the building block of every puff. This cornmeal is then enriched with a blend of vitamins and minerals, including riboflavin, niacin, iron, and folic acid. The enrichment not only helps meet nutritional labeling requirements, but also contributes to uniformity in the extrusion process, as these additives influence how the mixture reacts under heat and pressure. The resulting product is a dry, golden yellow flour with a specific granulation profile tailored to the plant's extrusion parameters. Before it is used on the production line, the cornmeal is stored in temperature and humidity-controlled silos directly connected to the processing plant. These silos often hold hundreds of metric tons of product and are designed to keep the cornmeal in a stable state for extended periods. Pneumatic systems transfer the cornmeal through stainless steel pipelines to weigh hoppers on the factory floor, where batch sizes are precisely measured. Real-time inventory sensors track the flow of material and communicate with the factory's central control system to automatically replenish supply lines as needed, ensuring uninterrupted production. Now it's time for the first transformation phase: hydration and preconditioning. The cornmeal is metered into a continuous mixing system where it is blended with water or steam to raise its moisture content to a narrowly specified range, usually between 15% and 20%. This step is essential to prepare the starch molecules for gelatinization. The equipment used here is not unlike a ribbon blender or paddle mixer, which agitates the mixture thoroughly to ensure every granule of cornmeal is evenly hydrated. Water is introduced through atomizing nozzles positioned at calculated intervals along the mixer's length, and multiple moisture sensors along the pathway feed back to the PLC system to adjust water input in real time. This moist mixture, often referred to as dough, despite its loose, crumbly texture, is held briefly in a conditioning tank to allow for even moisture distribution. The temperature and residence time are carefully controlled. If the mix is too hot or too wet, it may pre-gelatinize and clog the extruder. too dry, and it won't expand properly. During this stage, the product is slowly moved along a jacketed screw conveyor that maintains a consistent temperature and prevents clumping. Now we arrive at the heart of the production line, the extruder. Industrial Cheetos are made using a twin screw extruder, one of the most sophisticated and critical machines in the plant. The twin screw configuration allows for highly controlled processing of the corn mixture, providing better mixing, higher shear, and superior control over temperature and pressure compared to single screw models. The hydrated cornmeal is fed into the extruder barrel, where it encounters two rotating screws that convey the material forward under intense mechanical pressure. External heaters line the barrel and raise the temperature incrementally as the product moves through each zone. Inside, shear forces generated by the screws convert some of this mechanical energy into heat, further increasing the temperature of the dough. The intense conditions inside the extruder, pressure in the range of 200 to 500 psi, and temperatures from 130 degrees Celsius to 180 degrees Celsius, cause the starches in the cornmeal to gelatinize and the water to superheat. The dough undergoes plasticization, becoming a molten mass under pressure. As this molten dough reaches the end of the barrel, it is forced through a die, the precision-crafted metal plate that defines the shape of the puff. The die hole is round and small, but as the dough exits into atmospheric pressure, the superheated water in the mixture flashes into steam, causing the structure to puff and expand dramatically in a fraction of a second. This rapid expansion is responsible for the iconic airy texture of a Cheeto. Just outside the die, rotating knives spin at high speed, slicing the continuous stream of puff into uniformly sized segments. The speed of the knives determines the length of the puff, while the pressure and temperature within the extruder affect its diameter and density. But even after this high-tech transformation, the newly extruded Cheetos are far from finished. They are still pale, moist, and bland, essentially unseasoned corn puffs. The next stage is all about turning them into the crunchy, craveable snack that consumers instantly recognize. First, the extruded pieces are conveyed via vibrating trays to a frying system. Here, they're submerged in hot oil, typically corn or canola oil, at carefully controlled temperatures ranging between 160 degrees Celsius and 180 degrees Celsius. The residence time in the fryer is only about 20 to 40 seconds, but in that time, the moisture content is reduced dramatically from around 15% to under 2%. This not only creates the final crispy texture, but also deepens the color slightly, giving the snack its characteristic golden hue. The fryer itself is a marvel of engineering, equipped with multiple sensors and filtration systems. Oil turnover rates are high, meaning that fresh oil is constantly added, while spent oil is removed and filtered to maintain quality. Skimmers remove any floating particles, and oil chemistry is monitored for signs of oxidation, free fatty acid levels, and polymerization. If any readings fall outside of the strict parameters, the fryer automatically triggers corrective actions, dosing with fresh oil, increasing filtration, or even pausing the line to prevent compromised batches from continuing downstream. After exiting the fryer, the Cheetos are carried on mesh conveyors through an air cooling tunnel. High-powered fans blow ambient or conditioned air over the freshly fried snacks, bringing them to a safe handling temperature and ensuring any surface oil solidifies just slightly to help the seasoning adhere. These cooling conveyors are extended and designed with soft vibratory motion to prevent breakage, ensuring that the delicate puffs remain intact before entering the seasoning phase. Next, the Cheetos are transferred into a massive rotating flavor drum, where their bland exterior is transformed by a shower of powdered cheese blend. But before we dive into the complexities of seasoning, we'll need to explore how oil coating is applied for adhesion and how powder distribution systems are calibrated to ensure every single puff gets the perfect amount of flavoring. This next part of the production process is where precision meets sensory science, and the result is the addictively cheesy snack that has become a global favorite. Now it's time to dive into one of the most iconic and intricate stages in Cheetos manufacturing, the flavoring phase. This is where the bland, puffed, and fried corn kernels are transformed into the intensely savory, cheese-coated snacks recognized all over the world. The process of seasoning Cheetos is not merely about tossing on a bit of cheese powder. It is an engineered, tightly controlled operation that determines product consistency, taste balance, visual appeal, and even mouthfeel. Everything from the size and porosity of the puff to the electrostatic charge of the powder particles is taken into account in this phase. After exiting the cooling conveyor from the fryer, the puffs are transferred into large rotating cylindrical drums called flavor tumblers. These drums are typically positioned on a gentle incline and rotate slowly, creating a continuous cascade of puffs inside the drum that exposes every surface area of each piece as they tumble forward. This mechanical tumbling is crucial. It ensures an even coating without crushing the fragile, aerated product. Inside the drum, two key applications occur almost simultaneously. First, a fine mist of oil is sprayed onto the hot puffs. Then, a controlled stream of seasoning powder is dispensed over the tumbling mass. The oil, which is typically a neutral vegetable oil like corn or canola, plays several roles in this step. Primarily, it acts as an adhesive layer that allows the seasoning powder to stick effectively to the puff's surface. Additionally, it helps activate the flavor compounds in the powder blend, carrying volatile aroma molecules and enhancing taste perception. The oil spray system uses ultra-fine atomizing nozzles that are precisely calibrated to deliver a uniform coat without oversaturation. Too much oil, and the puffs become greasy and soggy. Too little, and the powder won't adhere properly, leading to uneven seasoning distribution and flavorless bites. The timing, angle, and rate of oil application are closely monitored and adjusted by sensors and programmable logic controllers. Real-time feedback systems measure oil usage, droplet size, and the thermal signature of the puffs to ensure that coating is optimal under varying production speeds or ambient conditions. This level of automation ensures consistency across thousands of pounds of product produced per hour. As the puffs are coated in oil, the seasoning powder is introduced using a vibratory feeder or screw conveyor system. The powder is held in a hopper mounted above the flavor drum and is dispensed through controlled openings at a fixed rate, matched to the flow of puffs. The exact dosing rate depends on the type of Cheetos being produced. Flamin' Hot varieties require slightly more powder per unit than the traditional cheese puffs due to differences in density, powder, granularity, and flavor intensity. The seasoning blend itself is a complex formulation engineered not only for taste, but also for flow characteristics, adhesion, and shelf stability. The base of the powder is often dehydrated cheddar cheese, spray-dried into a fine particle form. This is combined with whey or whey protein concentrate, maltodextrin, salt, monosodium glutamate, MSG, disodium phosphate, citric acid, and natural or artificial flavors. Each of these ingredients plays a very specific role. Maltodextrin, for example, acts as a carrier and anti-caking agent that helps the powder distribute evenly and resist clumping. Citric acid provides a tangy bite that enhances cheese flavor. MSG boosts umami and deepens savory perception. Color additives like annatto or oleoresin paprika for classic cheese and red 40 or yellow 6 for Flamin' Hot are oil dispersible pigments that give the snack its vivid appearance without creating spotting or streaks. The particle size distribution of the powder is engineered to align with the surface texture of the puffed snack. Powder that's too coarse will fall off, and powder that's too fine will clump or create an overly dusty texture. To prevent powder fallout, Electrostatic systems are sometimes used in high-speed lines. In these cases, the powder is given a minor static charge to improve its affinity for the puff surface, minimizing waste and improving adhesion. Inside the flavor tumbler, the balance of oil spray and powder distribution creates a beautiful, uniform layer of seasoning that fully coats each puff without pooling at the bottom of the drum or leaving bald spots on the product. The drum's internal design is key. Angled baffles gently lift and drop the puffs to keep them moving without subjecting them to mechanical stress. As the snacks make their way to the end of the drum, they are now visually and sensorially transformed. Bright orange, evenly coated, and bursting with aroma. Once the seasoning phase is complete, the fully flavored Cheetos are gently transitioned to the final conveyor belt systems that lead to the packaging area. Here, another series of quality control measures come into play. Inline camera systems inspect color uniformity and powder coverage using advanced image recognition algorithms. If a section of the product stream is detected to have an irregular appearance, whether due to light seasoning, overcoating, or discoloration, it is flagged and diverted from the main line for manual inspection or disposal. At this point, the Cheetos are still vulnerable to moisture pickup, oxidation, and mechanical damage, so the packaging process must move swiftly and with precision. The conveyor system delivers the finished puffs to a multi-head weigher mounted above the bagging machines. This machine uses multiple weigh hoppers to rapidly measure exact product portions, typically in the range of 28 g to 250 g per serving, depending on the bag size. These weighers use real-time load cell feedback to select the optimal combination of buckets to match the target weight, within a tolerance as tight as plus no 2g. Each pre-measured portion is released down a chute into a vertical form-fill seal (VFFS) machine. These machines work by pulling a flat roll of pre-printed film through a collar that forms it into a tube. The bottom of the tube is heat sealed to create the first seam, the Cheetos are dropped in, and then the top is sealed and cut, simultaneously forming the bottom seal of the next bag in line. These machines can fill and seal over 100 bags per minute per lane, and multiple lanes often run in parallel for large-scale production. The film used for the packaging is multi-layered and engineered to provide barrier protection against light, oxygen, and moisture. It typically includes an outer polyester film for print quality and visual appeal, a middle layer of aluminum or metallized polypropylene for oxygen and light resistance, and an inner polyethylene layer for heat sealing and moisture resistance. As each bag is sealed, a date code, batch number, and factory identifier are printed using high-speed inkjet printers for traceability. Just after sealing, every bag passes through a series of checkpoints. Metal detectors scan for any foreign objects. Vision systems verify print alignment and code readability, and weight checkers ensure compliance with regulatory standards. Non-conforming bags are automatically ejected onto a rejection conveyor, where they are set aside for manual inspection. Approved bags are then grouped and packed into cardboard shipping cartons by robotic pick-and-place systems or automated drop packers. These cartons are sealed, barcoded, and routed to the palletizing station. Here, industrial robotic arms stack the cartons onto wooden or plastic pallets using optimized patterns for stability and load balance. As each pallet is completed, it is wrapped in stretch film to secure the load and protect it from dust and humidity during storage and transportation. The palletized loads are then scanned into the plant's warehouse management system, which tracks location, batch status, and distribution destination. Some pallets are moved to ambient storage if they are designated for short-haul routes, while others are transported to climate-controlled storage areas that maintain low humidity and consistent temperatures, ensuring that the product maintains its texture and flavor until it reaches its final destination. What follows is the outbound logistics phase, where the pallets are loaded onto trucks, routed to distribution centers, and delivered to retailers. But for now, every step inside the production facility, from the moment the cornmeal is hydrated to the final bag, passing the last inspection point, has been a meticulously engineered series of chemical, mechanical, and sensory transformations. Every component of the Cheetos production line is designed not just for efficiency and speed, but to deliver a reliably indulgent experience in every bag. And it all happens in a continuous, automated, high-output environment that must maintain exacting standards of quality, cleanliness, and consistency hour after hour, shift after shift. One of the key operational pillars at this stage is environmental control. Temperature, humidity, and airflow within the production zones are tightly monitored and controlled around the clock. Cheetos, especially after frying and seasoning, are highly sensitive to ambient conditions. If the air in the seasoning or packaging area carries too much humidity, for instance, the cheese powder may begin to clump, reducing its dispersibility and leading to uneven coating. Worse still, excess moisture can cause the puffs to begin absorbing water from the air, softening the texture and compromising the crisp, dry bite expected by consumers. To prevent these issues, HVAC systems specifically engineered for food processing environments are deployed throughout the Cheetos plant. These systems do more than just heat or cool. They dehumidify, filter, and exchange the air in sensitive zones at rapid intervals, ensuring a constant flow of purified, dry, temperature-stabilized air. Some areas, such as the seasoning tumblers or the vertical form-fill seal zone, may be isolated with positive air pressure to ensure that external air, dust, and contaminants do not seep into these critical zones. These environmental systems are integrated with digital controls that feed data into the facility's central monitoring hub. Temperature and humidity data are tracked every few seconds, and if any reading moves outside of pre-programmed tolerances, automatic alarms notify technicians to investigate immediately. In some cases, the system will even halt upstream processes automatically to prevent production under unsuitable conditions, protecting product quality. While environmental controls maintain external conditions, another system ensures the quality of what's happening on the line, inline quality assurance, and real-time analytics. Throughout the Cheetos line, from extrusion to bagging, dozens of sensors, scanners, and cameras work in unison to gather data on key quality metrics. These include moisture content, oil absorption rate, puff size, color uniformity, seasoning coverage, and weight per unit. Each of these factors contributes not only to taste and mouthfeel, but to customer satisfaction and regulatory compliance. Advanced laser micrometers and stereo imaging cameras measure the dimensions of each puff as it moves across the line at high speed. If puffs fall outside the programmed size range, either due to inconsistent extrusion pressure, die blockage, or improper cutting, those units are flagged and rejected automatically using pneumatic diverting arms. Simultaneously, optical sensors inspect the color of the fried puff to confirm it matches brand-specific targets. Color variation could indicate improper frying time, fluctuating oil temperature, or oil degradation. The system will trigger alerts or shut down sections of the line if it detects drift from acceptable limits. Another important part of inline quality is the metal detection system. Every snack must pass through high-sensitivity metal detectors or, in some cases, X-ray systems just before packaging. These devices scan for trace amounts of ferrous, non-ferrous, and stainless steel contaminants which could originate from worn machinery parts, upstream, or during maintenance. The sensitivity of these machines is such that they can detect metallic particles smaller than a millimeter in diameter. If a contaminated bag is identified, it is automatically ejected from the line, recorded in a digital log, and sent for root cause analysis. In high-output snack manufacturing, product changeovers are another critical concern. A single plant might produce multiple Cheetos variants: classic cheese, flamin' hot, jalapeno cheddar, and limited editions on the same line, sometimes switching several times per day. To avoid cross-contamination of flavor profiles and allergens, the factory must execute a full product changeover, which includes both physical and procedural steps. The final bags of one variant are run through the line until the seasoning and product types are completely cleared. Following that, dry cleaning and wipe down protocols are enacted on exposed surfaces. In flavor tumbler zones and powder feeding systems, residue removal is handled by a combination of mechanical vacuums, compressed air nozzles, and in some cases, wet cleaning cycles. Pipes carrying seasoning powder are often disassembled and cleaned manually or flushed with air-driven pigs, foam or rubber projectiles that scrape the interior of the tube clean as they are propelled by compressed air. All cleaning steps are verified through ATP, adenosine triphosphate, swab tests or allergen-specific strip tests to confirm the line is ready for the next product. Equipment cleaning and sanitization extend far beyond changeovers. Each section of the production line is scheduled for deep cleaning on a regular basis, with some components cleaned daily, others weekly, and critical systems, like oil fryers, undergoing monthly shutdowns for intensive maintenance. Every cleaning task is documented in a digital sanitation log that includes time-stamped photos, chemical usage records, technician ID, and verification by a supervisor. This log ensures compliance with food safety regulations and internal auditing systems. Speaking of oil fryers, one of the more maintenance-intensive systems in the Cheetos plant is the oil management setup. Used frying oil is constantly cycled through multi-stage filtration systems that remove fine particulates and oxidized residues. Inline sensors monitor oil color, free fatty acid content, and total polar compounds, all indicators of oil degradation. When thresholds are approached, fresh oil is introduced, and a portion of the old oil is purged to waste recovery tanks. This spent oil is not discarded haphazardly. Instead, it is captured and sent to third-party processors who refine it for use in biodiesel production or industrial lubricants, creating a closed-loop waste management process that supports sustainability goals. Seasoning systems have their own challenges in terms of dust and waste control. Cheese powder and spice blends are notoriously airborne, so extraction hoods fitted with HEPA filters are positioned above tumblers and conveyors to capture stray particles. These systems not only keep the air clean for workers, but also prevent buildup on surfaces and reduce cross-contamination risk. Powder recovered in this way is not reused in production, but is collected and weighed for waste tracking. Many factories monitor seasoning powder yield versus usage to optimize application and reduce excess without compromising flavor intensity. Additionally, factories employ floor-level waste segregation systems, where organic waste, such as broken puffs or overcooked batches, is separated from packaging materials and cleaning byproducts. Organic snack waste is often sent to animal feed processing plants or used in anaerobic digesters to generate energy, while plastics are compacted and shipped to recycling partners. These systems not only reduce landfill usage, but also lower the facility's total environmental impact per unit of product. Every phase of the factory's operation is governed by a robust system of documentation and auditing. Real-time production data is logged into the Manufacturing Execution System, MES, which connects to the plant's Enterprise Resource Planning, ERP, platform. This system allows plant managers to track every batch of Cheetos from cornmeal input to palletized output. If a quality issue is flagged post-distribution, every input, cornmeal batch, oil lot, seasoning blend, even the operator ID can be traced within seconds. This level of transparency is essential for large brands that operate under continuous scrutiny from regulators, retailers, and consumers alike. All these systems, from the air handlers and fryers to the conveyors and flavor blenders, are monitored by a central control room staffed by trained process engineers and operators. The control room acts as the nerve center of the factory. Touchscreen interfaces display real-time data on line performance, yield percentages, waste figures, and energy usage. Alarms and alerts notify the team of any deviation in pressure, temperature, fill levels, or machine health. The staff can make remote adjustments, schedule maintenance tasks, and even initiate partial or full shutdowns directly from their stations. In many facilities, predictive analytics platforms are integrated into these systems. Using machine learning algorithms, these platforms analyze historical and current data to forecast when a component might fail, how yield might shift under ambient changes, or what impact a change in oil temperature might have on puff expansion. This allows for proactive decision-making, reducing downtime, and maximizing efficiency. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification. and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers, and the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package.